All right, so now we're going to talk about mutual information. So let's consider a situation with two random variables. Let's denote them by x and y. And the manifold consists of all probability distributions. It's like on this joint set of random variables. Okay. So you probably know that if the two random variables are independent, right? So when x and y are independent, what that means is that you can write this probability distribution in x and y as the product of a probability distribution in x and a probability distribution in y, right? So px x times py y, for example, right, where px and py are the marginal distributions. And of course, what that just means is that px involves integrating pxy over the other variable y, and pyy involves integrating pxy over x, right? So that's what's meant by the marginal distributions. Okay, so we're looking at a situation that's like where you have a joint probability distribution, which happens to be just the product of two marginal distributions. And that corresponds to a situation where the x and y variables are independent. Okay? So one way to think about it then is that in this space of joint probability distributions on x and y, there is a submanifold that's like of probability distributions which are independent, which is to say they're in this kind of product form, right? So it's like a separation of variables, if you will, right? So let mi denote the family of all independent distributions. Okay. So let's make the following observation about this family of independent distributions. So observe that the exponential family connecting two independent distributions is again independent. So what that basically means is that this, it's like submanifold. It's like of independent distributions embedded within the space of all joint probability distributions is E flat, basically, right? So Mi is an E flat submanifold. Okay. So now you can ask sort of more generally, right? If you had a general joint probability distribution, how far it is from this family, it's like of independent distributions, right? And as you might expect, it's like the distance, if you will, how from that probability distribution, it's like to this family, the submanifold, it's like independent distributions. It's going to tell you something about the mutual information it's like between these two random variables. Okay. So let's see what happens. So given a non-independent distribution, let's call it pxy, right? We want to find the closest independent distribution. In the sense of KL divergence. So again, this is sort of essentially a closest point projection, right? And you should observe that this sort of closest point projection in the sense of KL divergence corresponds to what's called M projection, right? So this corresponds to M projection of this probability distribution Pxy, right, to this submanifold of independent distributions. Okay. So this projection turns out to be unique. And it's given by this expression. P hat xy is just the product of the marginal distributions. Pxx, Py, y. Okay. All right. So, so you can ask, well, what is the divergence? What's the KL divergence between the probability distribution Pxy? It's like and this projection, which is the product of the marginals, right? So the KL divergence between Pxy and its projection is as follows, right? So dKL between P xy and P hat xy, right, is given by the integral from of Pxy log Pxy divided by P hat xy dx dy. And this, of course, is just the mutual information of the two random variables. xy. So another way to sort of think about this is that the mutual information measures the extent to which you have a probability distribution which deviates from dependence, right? So mutual information is a measure of discrepancy of this probability distribution from independence. Okay. All right. So you can ask the reverse as well. All right. So you can ask the reverse question. Which is as follows, that if you're given an independent distribution, find the distribution Pxy which maximizes the mutual information and of course you have to constrain that, right, in some way. So you want to maximize this over the class of distributions with the same marginal distribution, right? Okay, so let's call that independent distribution p hat. Okay, the same marginal distribution. As p hat. Okay. So it turns out that this is the inverse image of the M projection. So these, as you might expect, okay. And this was studied by a number of authors, which I won't go into. Okay. All right. So anyway, so that gives you, it's like a way to relate mutual information to sort of a geometric measure, if you will. It's like which tells you, for example, the KL divergence. It's like between the given probability distribution which you're working with and this submanifold. It's like of independent distributions. So let me just stop here for now.